Hello everyone and welcome to our second lecture in groups. We're going to start off by talking about something called a group table. If G is a finite set and G together with the binary operation star is a group, it is often convenient to define a binary operation star on G by constructing a group table. The group table is a square table in which both the rows and the columns are headed exactly once by each element of the group. If A and B are elements of the group, then the entry in the row that's headed by A and the column that's headed by B is the element assigned to A star B. And remember, row first, column second, just like in linear algebra. So the entry in the row headed by the first element and the column headed by the second element is the entry that's assigned to the ordered pair AB. Let's look at an example. Consider a group G star where the group G contains four elements, E, A, B, C. And E, traditionally, we let that be the identity element. This is what the group table for G would look like. E is a header for this. This is the header for the first row of the table. And this header indicates that all of the elements are elements that are assigned to ordered pairs where E is the first element of the ordered pair. A is the header of the next row, and in this row, A is the first element of the ordered pairs in this row. B is the header for the third row, and this indicates that all of the elements in this row are such that B is the first element of the ordered pair in this row. And C, this is the header for the last row. This row is the row in which C is the first element of the ordered pairs in this row. Similarly, we have column headers. This is a column header for the first column, and this indicates that E, the identity, is the second element of the ordered pair in this column. In the second column, A is the header, and A is the header indicates that A is the second element of the ordered pair of every ordered pair in this column. B heads the third column. B is the header of the third column. And this indicates that the second element in every ordered pair in this column is B. And then finally, C heads the last column. And the fact that C heads this column indicates that C is the second element of the ordered pair. Whoops, I don't like that. I must have been on autopilot when I wrote this, right? This is definitely not what I need here. This is the element C times C. Row C, column C. As a matter of fact, since I just said that, why don't we also acknowledge what each of these elements represents? This is the element in the row headed by E and the column headed by A. This is the element in the row headed by B and the column headed by A. Remember, row first, column second, just like in linear algebra. This is the element in the row headed by C and the column headed by A. This is the element in the row headed by A and the column headed by B. This is the element in the row headed by B and the column headed by C, and so forth. Now, I'm going to remake this table, and instead of putting the ordered pair with the binary operation in between, I'm going to put the element that's assigned to each ordered pair by the binary operation. Here's an example of a group table where the elements are given explicitly. And let's just see what some of these elements are. Since this is in the row headed by E and in the column headed by A, this is the element E star A. And let's pick this one. Since this is in the row headed by E and the column headed by B, this is E star B. And over here, since this is in the row headed by B and in the column headed by E, this is the element B star E. Since this is in the row headed by C and the column headed by A, this is the element that's assigned to C star A. This element is in the row headed by C and in the column headed by B, so this is the element assigned to C star B, and so forth. Now we might notice something. As a matter of fact, this probably jumps right out at us. The first row of the table is exactly the same as the row of column headers that appear above it. So the first row is a copy of the row of column headers that appear above it. And something similar happens in the first column. In the first column, the elements are exactly the same as the column of row headers that appear to the left. Each element in column 1 is the same as the row header that appears to the left. And this is just a reflection of the property that the group identity has. This element is E star E, and the identity, when we multiply it by anything, gives us anything. So E star E is E, E star A is A, E star B is B, E star C is C, because the identity has the property that E star anything is that anything. And a similar thing happens in the first column. This is E star E, so we get E. This is A star E, so we get A, because anything star E is that anything. A star E is A, B star E is B, C star E is C. That's the property that a group identity has. So that's the way it works out. By the way, I did mention a minute ago that it's customary to have the identity head the first row, and it's customary to have the identity head the first column. It's also customary to have the elements of the group listed in the same order in the row of column headers and in the column of row headers. So the order of elements across the top in the row of column headers is exactly the same as the order of elements in the column of row headers. And so the first row of the table essentially will be a copy of the column headers that appear above. The first column of the table will be a copy of the row headers that appear to the left. All group tables are set out in that manner. And the order of the elements across the top is exactly the same as the order of elements in the left column of row headers. Now let's look at another group table. Here's another example of a group. Interestingly enough, what we call the set of elements H, even though it turns out that the set H and the set G are one and the same, but this is going to be a different group, so we'll call it set H. And we know across the first row, the elements in the first row are exactly the same as the column headers that appear in the row of column headers across the top. And in the first column, the elements are exactly the same as the row headers that appear in the column of row headers to the left. Let's just identify where some of these elements come from. This is in the row headed by E and the column headed by B, so this is E star B. This element is in the row headed by E, the column headed by C. So this element is the element that's assigned to E star C. Now let's see. This element is in the row headed by B and in the column headed by B. So it's the element that's assigned to B star B. This element is in the row headed by C and the column headed by A, so this is C star A. And let's pick on this element. This element is in the row headed by B and the column headed by C. So this is the element assigned to B star C. And let's pick one more for good measure. Let's pick this guy. This is in the column headed by A. This is in the row headed by A and in the column headed by B. So this is the element that's assigned to A star E. Now we might notice some similarities in the two tables and some differences in the two tables. And I think I want to talk about this now. Let me just make sure. I'll check my notes. Let me apologize for being stupid. This example of H wasn't the one that I wanted to give, but I didn't notice it until I hit the pause button and turned around and looked at both groups. It was beneficial just for the sake of pointing out which each element in the table represented. For example, this represents the element that's assigned to the ordered pair A star E, and this represents the element that's assigned to the ordered pair E star C, and so forth. H is history. Nothing wrong with it, but it's not really what I needed to talk about at the time. So we'll talk about group K. And oddly enough, K is the same set as G, but it's a different group. And there's something structurally different about this group compared to this group. And when I say structurally different, I cannot get this group from this group simply by renaming the elements. So this table has an algebraic property that this group table doesn't. Let's see what that is. Does anybody see anything distinctly different about this table compared with this table? And if we do, we're probably focusing on the fact that we have the identity element right down the main diagonal. So this, of course, is E star E. Since this is in the row headed by A and the column headed by A, this is A star A. Since this is in the row headed by B and the column headed by B, this is B star B. And since this element is in the row headed by C and the column headed by C, this is C star C. Now, when we have two elements that are assigned the inverse, that means that each of these elements is the inverse of the other. And in our first group table, we had row A, column C, so this is A star C. Well, the element assigned to A star C is the identity, which means that C is the inverse of A, and A is the inverse of C. And here we have the identity appearing in the row headed by C and the column headed by A. So the identity E is the element that's assigned to the ordered pair C star A. So again, A is the inverse of C, C is the inverse of A. What about over here? This is in the row headed by C and the column headed by C. So this is the element, the identity, that's assigned to C star C. In other words, C is its own inverse. C is the inverse of C. Here we have the identity appearing in the row headed by B, in the column headed by B. So E is the element that's assigned to B star B. In other words, B is the element that we multiply B by to get the identity. So B is the inverse of B. And similarly here, E is the element assigned, E, the identity, is the element assigned to A star A. So A is the inverse of A. Now do we see the property that this table has? It's something the other table doesn't have. In this table, each element each element is its own inverse. That doesn't happen here. For example, C star A is the identity. So A is the inverse of C, C is the inverse of A. So in this table, it's not true that every element is its own inverse. These two tables are structurally different because the elements have different algebraic properties. The elements plus the binary operation here have different properties than the elements in the binary operation here. So the two groups are structurally different. We can't get this group from that group just by taking the elements of this group and renaming them. These two groups are structurally different, but they do have an algebraic property in common. Even though they're structurally different, they do have an algebraic property in common. And I think what I'll do is I'll redraw the group, both group tables, without all of this scratch work on it, just so that we can look for the algebraic property that both of these groups have in common. Okay, I've redrawn the group tables, and I'm going to draw what in linear algebra we would call the main diagonal in each table. And we might notice something in both tables, namely that each table is symmetric about the main diagonal. The elements below the main diagonal are the image or the mirror image of the elements in the corresponding position above the main diagonal. For example, we have A and A, and here we have B, B, and here we have C, C, and C, C, E, E, A and A. Pick any element below the main diagonal and go to its mirror image above the main diagonal. We get the same element. Another way of looking at this is that if we take an element in the table and reverse the row in the column, we get the same element. For example, this is row C, column A. This is row A, column C. Same element. Row C, column E. This is row E, column C. Same thing happens over here. Even though the table is structurally different, it does have the same thing in common. B, B, C, 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 E, E, A, and A. But take this element. It's in row B, column A. If we switch the row in the column and go to row A, column B, we get the same element. This element, it's in row C, column A. And if we switch the row in the column and go to row A, column C, we get the same element. Switching the row and the column, that means we switch the order of the pair. So in other words, for each x and y in G, x star y equals y star x. And same thing here, for each x, y in K, x star y equals y star x. In other words, the row that's in the element that's assigned, the element that appears in row x in column y is the same as the element that appears in row y in column x, which means that the operation is commutative in both cases. If a binary operation is commutative, it will show up in the group table. The group table will be symmetric about the main diagonal. So both of these groups have the property that the binary operation is commutative. If the binary operation is commutative, then the table will be symmetric about the main diagonal. And if the group table is symmetric about the main diagonal, then the operation is commutative. And we'll talk more about that in just a minute.